Finally, we discussed the null implementation, and we note also that the null gate is referred to as the universal gate because it can be used to implement any logic function. And in order to synthesize a logic expression with null gates, it is desirable to express it using the POS form. We notice that with the NAND gate implementation, we expressed our solution or our expression in SOP. This is for the NAND implementation. But with the null implementation, it is best or desirable to express our Boolean expression in using the POS form so that we can use the null gate as a universal gate to express or to solve or to implement our solution or our expression. For example, we have this example that says that we will have our expression y given by a or b or c bar or dot a bar or b bar dot a or c. So if you are to do that expression using the null operation, again, the best way is to do the same. Introduce double bars. I'm going straight to the point, and then break this line, change the sign, becomes all. Break this line, change the sign, becomes all. So this becomes a null operation, this becomes a null operation, this becomes a null operation, and the overall operation, null operation, and any inverters are given. Again, we notice that if you short the inputs of a null gate, you will get a NOT gate. So if this was an A, what will come out here will be a NOT A. And for that reason, we simply end up with the function that is represented by. So this is first and foremost, we want to represent this function using the invert, all, and add gates, and this is the one that is represented by this diagram. But now we are saying we want to have the null equivalent of this circuit. And as I have shown, all we need to do is to introduce double bars, then we apply the De Morgan's theorem, break the first bar up to this point so that we have a plus there, and a plus there, and a plus there, and then another one. Remember when we said that two double bars are the same, they cancel one another. So we only now apply the De Morgan's theorem to modify the inner bar. So this becomes a NOR, and the overall NOR, and every NOR inverted gate can be implemented with a NOR gate whose inputs are shorted. So the final expression of our gate will be seen shortly with a null circuit. In order to convert the circuit to an implementation with null gates, it can be observed that the invert gate is equivalent to a null gate whose inputs are shorted. That is something I have already said, and that our OR add circuit is equivalent to a null circuit that we have seen. And therefore, finally, the OR gates and the add gates are substituted with null gates. And here we have our diagram that represents the implementation of our circuit using the null gates only. So this is very significant because we might be told we do not have any other gates apart from null gates, and therefore we can be able to convert our invert, or an add gate to a circuit that can still perform the same function using only one type of gate called null gate. So another example that I think it would be good if I just showed you, assume you are given y is equals to a or b, and you want to perform this using null gates only. For me, all I will need to do is to introduce double bars, and this becomes a null operation, and then at the end you will be able to have another null gate that performs the inversion or inverts this input. This would now become the first null gate. This becomes A, B. What you get out of here is A or B bar, but you take this through another in or null gate. This becomes A or B because it performs the operation. Therefore, what you have been able to do is to achieve this circuit, this expression, using two null gates or one type of a gate. Maybe I should give you another example. Convert the following or implement y is equals to ab plus cd using NOR gates only. This is very simple. Introduce double bar to every product so that you can now break this line and change the sign. Break this line and change the sign so that we have y is equals to a bar or b bar bar. Then introduce another double bar at the top here. So what we'll do is that this becomes one invert. This is NOR operation. This is NOR operation with this bar. This is another NOR operation. This is a NOT operation. So this is how you do it. So you end up with how many NOR gates? 1, 2, 3, 4, 5, 6, 7, 8. Everywhere we have a bar, that means is a NOR operation. So the idea is the same. You would introduce double bars to break the product first, and then you introduce a double bar at the top for all of them so that you are able to perform the NOR operation.